Welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. Actually, this lecture is essentially the last lecture of this course. So, in this lecture we shall be talking about the general structure of the Jacobian matrix, followed by some example for a three-phase state estimation of an small unbalanced power system. So, we have already said that we said that when we are trying to do this state estimation, we have to calculate this matrix Hx. What is this matrix Hx? This matrix Hx is basically del z by del x. So, for examples, so suppose my z vector is, let us say, z1, z2 to zm t. Z vector is nothing but the measurement vector, and my vector x is nothing but x1, x2 to xn. This is the state vector to be estimated, xn. So, then hx is actually del z del x is nothing but del z1 del x1 del z1 del x2 dot del z1 del xn and then dot del zm del x1 del zm del x2 del xn. So, that is how. So, this is the case. Now, as we said that my z, my measurements can come only from 5 categories, that the categories are PIP, QIP, IIJP, magnitude, then PIJP and QIJP, and of course, sometimes we also measure the voltages. So, now suppose I do have, so now from this expression, now we said that this is some functions of only Vi ABC, theta I ABC, Vj ABC and theta j ABC of these vectors, and what these vectors are, that we have already discussed in the last class. Similarly, this is also a function of only these 12 quantities. Similarly, this is also a function of only these 12 quantities. Let us take an example. Maybe it will be easier. So, these are the lines, these are the buses. So, these are the these dark lines are bus. So, this is bus 1, bus 2, bus 3, and this is phase A, phase B, phase C. Now, suppose I have measured a quantity P23A. Suppose I have measured a quantity P23A. So, you see, so then therefore, from this expression P23A would be only a function of P23A would be only a function of V2ABC, theta 2ABC, then V3ABC and theta 3ABC, right. So P23A would be only a function of V2ABC, theta 2ABC, V3ABC, theta 3ABC. It will not at all be a function of any quantities associated with bus 1. That means it will not be at all a function of V1A, V1B, V1C, or theta 1A or theta 1B or theta 1C. Similarly, had there been some other buses also, say for example, if there is other buses also, bus 4, bus 5, so this P23A will not be also a function of any other quantities, that is, it will not be a function of V4A, V4B, and etc. etc. Correct. Similarly, if I, let us say, measure the Q23B, it will be also only a functions of V2ABC, theta 2ABC, V3ABC, theta 3ABC. And suppose I measure here I23C and its magnitude, suppose I measure it here, right. So, I have got, let us say, these 3 meters. The first meter is measuring P23A, second meter is measuring Q23B, third meter is measuring the magnitude of I23C. So, this is also will be a function of only V2ABC, theta 2ABC, V3ABC, and theta 3ABC, correct. But if I, suppose for example, if I measure, say, some injected quantities P3A, say, let us say this I, suppose if I measure P3C, correct. Now, following the expressions of PIP, we can see that the expressions of PIP includes the summation over all the buses, correct. So, then therefore, P3C would be a function of all the bus voltage magnitudes as well as the angle. So, then therefore, any injected quantity would be the function of all the bus voltage magnitudes and the angles, but any measured line quantities, either real power flow or reactive power flow, or let us say the magnitude of the current, would be a function of the quantities associated only with the two terminal buses, right. So, with this, now suppose I do have in this system, suppose I do have, so now for example, in this system, what are my unknown quantities? So, in this small system, my unknown quantities are V1 ABC, V2 ABC, V3 ABC, theta 1 BC. Please note theta 1 A is 0, then theta 2 ABC and theta 3 ABC. So, I mean, this is the state vectors, right. So, how many? 3 plus 3 plus 3, 9. So, 1, 2, 3, 4, 5, 15 plus 2, that is 17 cross 1. Right. So, suppose to do this, suppose I do have several measurements. Now, because there are 17 unknowns or rather 17 states, so I do have to have measurements over, at least I should have, let us say, I mean 17 measurements from somehow. Suppose for example, my measurements are P3C, Q3C, suppose P3C, Q3C, P3B, Q3B, P3A, Q3A. So, P3A, my measurement quantities are P3A, Q3A, then P3B, Q3B. So, from here I get 6, and here also for example Q23A, here also P23A, and here also this is B and P23C. Suppose, so this is 6, this is 6, this is 12, and then suppose for example from here also I get some other 6 quantities, right. So, let us say that this is P21A and Q21A, let us say this is P21B Q21B, and let's say this is P21C, Q21C. So suppose these are these 18 measurements I do have, right? So I do have got these 18 measurements, 1, 2, 3, 4, 5, 6. So these are the measurements, these quantities within this circles are the measurements. Suppose these are the measurements. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 into 2, 18. So I have got 17 states, 18 measurements. So then you see, for example, here in this case, what would be my hx? My hx would be, say, for example, P21A. Suppose I say that is my Z1 is, so del P21A by del V1, then del P21A by del V1A, del V1B, and then dot 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 del P21A by del theta 3C. So this is the first row, for example. Second row, suppose let's say this is corresponding to Q2A. Third row, suppose P21B. Fourth row, suppose Q21B, and so on and so forth. And let's say fifth row, and let's say the last row, suppose it is P3C. So the last row, for example, let's say write it down. So it is del P3C by del V1A, and then dot 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 del P3C by del theta 3C. So this is the case. Right, now you see del P21A. Now P21A would be only a function of V1 ABC, theta 1 BC, V2 ABC, and theta 2 ABC. So then therefore del P21A by del theta 3 ABC would be all 0, because it will not be a function of theta 3. Similarly, del P21A del V3 ABC will also be 0, because it will not be a function of any quantities associated with any other bus other than 1 and 2. So then therefore in general, del Pijp by del theta I ABC would be non-zero, right? And del Pijp by del VIABC would be non-zero. Then del Pijp by del VJABC would be non-zero, and del Pijp by del theta JABC also would be non-zero, because Pijp would be the functions of only VIABC, theta ABC, VJABC, and theta JABC. But del Pijp by del VKABC would be 0 for k not equal to I or j. Similarly, del Pijp by del theta KABC would be also 0 for k not equal to I not equal to j. Right. So, any other bus, they would be 0. Same conclusion also I can draw. for Qijp and Iijp magnitude, right? Same conclusion. So then therefore I can say that del Qijp by del Vkabc would be 0, also that is also equal to 0, as del Qijp by del theta kabc also would be equal to 0, where k is not equal to either I or equal to j, right. But for any other, but then del Qijp by del Viabc would be non-zero, del Qijp by del theta Iabc would be non-zero, del Qijp by del Vjabc would be non-zero, and del Qijp by del theta Jabc also would be non-zero. Similarly, I can say that del Iijp magnitude by del Vkabc would be is equal to 0, that is also would be equal to 0 by del theta kabc would be equal to 0 for any k not equal to I, not equal to j. That is also all will be equal to 0, because Iijp is only a function of Viabc, theta Iabc, Vjabc and theta Jabc. This is Iijp is not a function of any other quantity. On the other hand, if I have, let us say, P3a, right. So, what is P3a? P3a is basically, it is basically L is equal to A, B, C and J is equal to 1, 2, 3 in this simple let us say 3 bus system. In general it is n is the number of bus, n is the number of bus. So, it is V3a and then Vjl, then Y3jal cosine theta 3a minus theta jl minus alpha 3jal, right. So, this is the expression. So, you can see P3a is a function of all bus voltage magnitudes Vj, right. I mean j varies from 1 to n, and theta j l, j varies from 1 to n and l varies from labc, correct. So, then therefore, del P3a by any other voltage and magnitude would be basically dependent on the value of y3j al. If this is 0, then this particular partial derivative would be 0. If this is non-zero, then this particular partial derivative would be non-zero. So, then therefore, P3a, so then similarly I can write down that PIP is basically a sum function of, it is the function of V1 ABC, then Vn ABC. In general, it is a function of this, and then theta 1 BC, theta 2 ABC, and then theta n ABC. So, this is a function of PIP is also a function of this. So, then therefore, any quantity del PIP by del VJL would be 0 or non-zero depending upon the value of Yijpl, right. In general there will be expression, but whether they will be 0. So, then expressions, so then I would say that this analytical expression exists. Of course, this we have already seen when we are talking about the load flow analysis. right? Similarly, for del PIP by del theta JL, also analytical expression exists. Whether they will be 0 or not, that will be dependent on the value of Yijpl. If there is, if bus I and j are directly connected, then there will be some value of Yijpl, so then it will be non-zero. If they are not directly connected, so then Yijpl would be 0. So then accordingly this expression also will actually turn out to be 0. After evaluation they will turn out to be 0, but analytical expression exists. Similarly, I can say that del QIP by del VJL and del QIP by del theta JL, for these also analytical expression exists. Right, for these also analytical expression exists. Please note, for the other cases when we are talking about this line measurements, either this real power flow over the line or the reactive power flow over the line or the current magnitude over the line, these are only the functions of the voltage and angles of the two terminal buses, right. So, these line measurements, they are not the function of any other voltage magnitude as well as the any other voltage angle. So, then therefore, the partial derivative of this line measurements with respect to any other non-terminal bus voltage magnitude or angles do not exist, because they are not a function. But PIP and QIP, they are function of all bus voltage magnitudes as well as the all bus voltage angles because of this expression. So, then therefore, their partial derivative. So, then therefore, in their partial derivative, this analytical expression exists. Whether there will be 0 or not, that all depends on whether this quantity Yijpl exist or not. For example, if bus 1 and, for example, here just to recollect, in this system, because bus 1 and 3 they are not directly connected. So, then therefore, in the overall Y bus matrix, this quantity Y13AA would be 0, because there is no direct connection. So, then corresponding elements of the Y bus matrix would be 0. So, that particular 3 cross 3 submatrix would be 0. I mean, all these details we have already discussed, right. So, then therefore, even if I try to find out the partial derivative of P3 and Q3A with respect to say V1A, V1B, V1C, they would be ultimately 0, because these two are not directly connected. But here you see, in the case of a very small network, we can perceive visually that which bus elements, I mean basically which bus is connected to which bus directly or not. But then for when we are talking about a large network, we really cannot perceive it, I mean visually, because there will be only data. So, we have to form this Y bus matrix by our computer code, and then accordingly following our algorithm, this Y bus matrix corresponding elements would be either 0 or non-zero, depending upon the case that whether these two buses are directly connected or not. Right. So, by this we do find out the expressions of Hx. Right. So, all these expressions I am leaving for an homework, because we have done so many, rather we have derived so many expressions of the Jacobian matrices when we are talking about the load flow analysis. So, then therefore, these expressions will also turn up, I mean are also the identical, almost same, basically the same process, only the algebra maybe will be essentially this little different. But of course, these expressions we have already derived with when we are talking about our load flow analysis. Similarly, these expressions also we have already derived, right, when we have talked about this load flow analysis. So these expressions we already know, and these expressions you have to derive it, but these I am again keeping it for you as a kind of homework, because this algebra would be much simpler. So it will be a fun. So, and then, so as we said that we do, so first you have to find out these analytical expressions of all the elements of this matrix, and then at every iteration we have to evaluate it and then do this Jacobian inversion and etc., etc. We have already said that what is the final algorithm. So now with this, let us look at a simple example. So this is a kind of distribution test system. So this is, so there are 5 bus system. So this is slack bus 1, bus 2, bus 3, bus 4 and bus 5. So this is in 3 phase unbalanced. So although this is basically single line diagram, but this is actually an 3 phase bus, right. So then therefore all these lines are essentially 3 phase lines. So with this, and this is basically the kind of specification. So this is an 11 kV 1 MVA power rating. So it is a radial network. Feeder sections are all 3 phase and unbalanced type. So we have considered loads at all the buses, and because these distribution systems, so we have neglected shunt charging susceptance. But then even if we consider shunt charging susceptance, it does not change the basic 3 phase state estimation algorithm, because this shunt charging susceptance of any line would be ultimately considered into the Y bus matrix of the system. And then so then therefore Y bus shunt admittance matrix is automated. So 3 cross 3 series. So then every line has got this corresponding 3 cross 3 elements, and you see we have already proved that for any unbalanced line, this line, I mean this matrix is always a kind of a symmetric matrix. So it is ZA, ZBB. So ZA and ZBA would be the same. And what is the quantity of this ZAB, ZBC, ZAC? These are also shown here, but then this is basically a symmetric matrix. And we have taken some measurements. For example, these are the power measurements here on this line, right. We have taken these power measurements, and then we have also measured these voltage magnitudes at all these buses, and etc., etc. And so now, and this is basically the line data, right. So bus 1 is the basically the slack bus, and then bus 2, 3, 4, 5, these are all PQ buses, and essentially they have got loads at every bus. So you see, for example, 150. So phase A kilowatt, phase A kVR 150, phase B kilowatt is 50, phase B kVR is 20, phase C 150. So then therefore this loading is also unbalanced in phase at bus 2. Similarly at bus 3 also this particular loading is unbalanced at bus 3, but bus 4 also this loading is unbalanced, but at bus 5 is also loading is unbalanced. So this is an unbalanced system. And this is the impedance matrix of this line. As you can see, this matrix is a symmetric matrix. And why this should be a symmetric matrix, we have already discussed in this lecture when we are talking about the derivation of the line impedance matrix ZABC. And these values matrices actually per unit length, uh, per unit length. So this is basically per mile, and 1 mile is equal to 5280 feet. And I have got 4 lines 1 to 2, 2 to 3, 2 to 4 and 4 to 5. So you see 1 to 2, 2 to 3, 2 to 4 and 4 to 5. So I have got these 4 lines. Please note, I mean this is not an bus. I mean this is basically bus 1, this is the slack bus. This is just a notation. So I have got only these 5 buses 1, 2, 3, 4, 5. So then I have got only 4 lines bus 1 to 2, 2 to 3, 2 to 4 and 4 to 5. So these are the, I mean line data. So their length is 2000 feet, 3000, 4500, right, 5000 feet, and we have already given this bus impedance, or rather we have already given this line impedance matrix in terms of per 5280 feet. So then therefore using this length we can calculate their actual impedance matrix of the lines. For example, the impedance matrix of this line would be this divided by 5280 into this line length, that is basically 2000, whatever it comes. Similarly, we can derive the line impedance matrix of this line for this line for this line. With this, then we take, so first we have to do the, now we have to take the measurement. So for measurements what we do, because we do not have any kind of physical measurement, so we first compute the load flow analysis of this system, right. So once we do this load flow analysis of this system, so we do get all voltage magnitudes, all voltage bus angles, and from these voltage magnitudes as well as the bus angles we can calculate any line real power flow, any line reactive power flow, any line current magnitude, etc., etc., right. So we first do this load flow analysis of this system, and for this we take a basically kind of flat start. So VABC is 1 per unit. So VA, VB, VC for all these buses are taken to be 1 per unit, and the angles we take the initial angles as 0, minus 120 degree, plus 120 degree, correct. And then we do compute this load flow analysis by this backward forward sweep method. Now this backward forward sweep method is, we have not discussed it because we have talked about only the transmission network in our lecture, in our in this course, but this particular backward forward sweep method is a very standard method in the case of distribution system analysis. So that particular method is not important. What we are trying to say, that by applying this method we have solved this load flow analysis, and after load flow these are the results. So for bus 1 it is one angle as, so 0 you see, but then for bus 2, 3, bus 4 and 5 these are not balanced, you see these are not balanced, okay. So these are not at all balanced. So although bus 1 this is always kept at one angle 0, one angle minus 120 degree and one angle plus 120 degree, but bus 2, 3, 4, 5 their voltage magnitudes are not balanced because of this unbalanced loading. So you see, so now with these voltage magnitudes and angles we have calculated all this power flow. So P1 to ABC is nothing but P1 to A, P1 to B, P1 to C, right. So similarly we have calculated the values of P23A, P23B, P23BC and so forth, so forth. So then therefore these are the all our measurement vectors, and my state vector is delta I ABC V1 IBC, right. So my total state variables would be 6n into 9. Please note that there are 5 buses, so n is 5. So my state variables is 6 into n minus 1, that is 6 into 5 minus 1, that is 29. N is number of buses. And total number of measurements is basically this much. So then total measurement redundancy is 1.758. What is mean by total measurement redundancy? Redundancy means it is the number of measurement divided by the number of state. So then therefore if we do count this number of measurements here, please note each of them denotes 3 measurements. So if I do count this number of measurements here and then divide it by 29, I should get this value 1.758. Then we follow this weighted least square state estimation technique, and then we take this flat start and we take the tolerance to be 10 to the power minus 6, and then we form the Jacobian matrix, etc., etc., etc. We follow this same process as we have said. So when we take these values, these ideal values obtained from the load flow analysis as the measurement values without adding any noise, and then do the state estimation and then recalculate this V IABC and theta IABC for all these 5 buses, we get these results, and these results are exactly matching the results of the load flow analysis. They should, because if there is no noise, so then therefore these measurements are ideal measurements. So then therefore these ideal measurements values should give me back the original voltage magnitudes and angles and what I have got. So then without any measurement noise, I will get the original load flow analysis values. But when I put some noise, and because you see we have already said that every meter has got some noise, so we have considered a noise of plus minus 3%. When I put some noise in all these measurements and add randomly a value of noise within this plus minus 3%, and then we do recalculate our state estimation, these are the results. You can see that these values are different that of the state estimate. I mean, these are the values, those are different from the actual load flow analysis values, which will be right. So the in the presence of noise, estimated values can never be equal to the ideal values, it is impossible. But because we don't have any measurement of these voltage magnitudes and angles directly, we are trying to do this state estimation. So we are estimating their values, and you see their estimated values are reasonably close. For example, here in the place of measurement for bus 2 phase A, the estimated value is 0.13111 degree, and what this ideal value is 0.1323. For bus 3 phase A, this angle is 0.2038, it is 0.2051, right. So although these estimated values are not exactly equal to the ideal values, but they are pretty close. So then therefore these values give us the reasonably good idea that what is the voltage magnitudes and what is the voltage angle of the system, and that is basically the idea of doing this state estimation. So with this we finish this lecture, and this is also the end of our course. Hope you have enjoyed this course, and hope this course proves to be of some value to all of you. Thank you very much all.